Hey guys, Arnav here with another video, and this might be a bit late for a couple of you, but just wanted to put it out there. And that's because most of you have probably already taken your Unit 2 test, but still better late than never, right? So yeah, today's concept is formal charge and resonance, and hope you enjoyed the video. Alright guys, let's start with our 3 J-pop song lyrics for today, which are Aotanatsu by Mrs. Green Apple, No Doubt by Official Hagedandism, and Walking With You by Novel Bright. So moving on to the academics, resonance basically emerges from the fact that there are some molecules for which we can draw multiple Lewis dot structures. And not to say that these are wrong, but they're not completely correct because they all contribute a little bit to what that molecule looks like in real life. So all of these individual renditions are known as the resonance structures, and then that real structure, or what the molecule would actually look like under a microscope and in nature, is called the resonance hybrid. So in AP chemistry, knowing now that what a resonance structure and what a resonance hybrid is, we are asked to find out which resonance structure contributes the most to the resonance hybrid. So in a sense, you could think of it as which one's the most correct. So let's use our example here for nitrous oxide. So there are 3 different nitrous oxide models that we can draw out, which are as follows, so A, B, and C. And the third one contributes the most to the resonance hybrid. And we know that because of another concept known as formal charges. So a formal charge is basically where you use this formula, where you take the number of regular valence electrons minus the number of valence electrons once bonded, and you calculate the formal charge for every atom within every molecule, and you do that for all the resonance structures. So it's quite tedious, right? But once you get done with it and you have a formal charge for all the atoms on every molecule, on every resonance structure, what you want to look for is which resonance structure has the least charge overall. And that one is going to be a resonance, or rather it's going to contribute the most to the resonance hybrid, right? So as I said before, it's not the best way to look at it, but it's technically the most correct, or the closest to being correct. Another technique to know is that sometimes you're going to have 2, or narrow it down to 2 resonance structures, and they will both have some charge on them, right? And the way you can pick which one contributes more here, in this case, is basically you want the more negative charge to be on the more electronegative atom. So that is kind of like this tiebreaker that we implement if 2 resonance structures still happen to have a charge towards the end. Before I move on to an example, I wanted to calculate with you guys how many valence electrons certain atoms have once they bond. Because contrary to what we might think, let's take this hydrogen here for example. Once it's bonded to this carbon, it has 1 valence electron, not 2. And that's because 2 are being shared and are present in this bond. Yes, you're correct in saying that. However, 1 comes from the hydrogen and 1 comes from the carbon because they're sharing them equally, right? So it is very important to notice that even though it's bonded, it's still going to have only 1 valence electron out of the 2 that are present in this bond. So let's do some calculations together. Ooh. Imagine you didn't see that, but how many valence electrons does oxygen have once bonded? So this one right here, oxygen. So we can see that it has 3 lone pairs. So off the bat, we know it has at least 6 valence electrons once bonded, and we have 1 bond. And since we just discussed about this, out of the 1 bond that contains 2 electrons, 1 of them belongs to oxygen. So the 6 plus 1, we get 7 valence electrons once bonded. Let's do that for this hydrogen down here. Again, here we have no lone pairs though, so keep that in mind. And instead we have 2 bonds. So that hydrogen is the owner of 2 electrons, 1 from each bond, and therefore we end up with it having 2 electrons once bonded. Alright, I hope that helped a little bit with how to calculate the number of valence electrons once bonded. Now let's do a practice problem, because these really help a lot and they really make the concept much more understandable. So I've written down, or rather drawn, all the resonance structures for you already for the cyanate ion, which is CmO-. And what I want for you guys to do is basically try and determine which of these resonance structures contributes the most to the resonance hybrid. So yeah, I've also given you the formal charge formula. So if you would like to use that, then do that, and let's try it. All right, so the formula is the number of regular valence electrons minus the number of valence electrons once bonded. So you take how many valence electrons that atom would normally have in the periodic table, subtracted by how many it has once bonded. So this oxygen here, this oxygen would normally have 6 valence electrons, right? And it has 1, 2, 3, 4, 5, and 6, one from each, after bonding. So 6 minus 6 is 0, and it has 0. Same applies for this carbon, which has 4 valence electrons normally. And again, we have 4 that it has once it bonds, so 4 minus 4 is 0. Now the nitrogen is where it gets interesting, because nitrogen normally has 5 valence electrons, right? But once it bonds, it has 1, 2, 3, 4, 5, 6. So 5 minus 6 is -1, and we get that -1 charge on this nitrogen. So now that we've done that one, let's move to the second one. This oxygen normally has 6, and then it has 1, 2, 3, 4, 5, right? Once it's bonded. So 6 minus 5 is +1. Carbon normally has 4, minus 1, 2, 3, 4. So 4 minus 4 is 0. And this nitrogen, again, as we discussed, nitrogen normally has 5. And in this case, it has 1, 2, 3, 4, 5, 6, 7. Ooh. So we should end up with a -2 charge here, a 0 charge there, and I believe a +1 charge there. Yep, so that's what we end up with. And let me try and give you guys some time to do the last one on your own, because I believe you can do it. Okay, I'm assuming that you've attempted it. So the charges that you should have gotten are -1, 0, and 0. So let's go over why that's the case. This oxygen, normally it has 6 valence electrons, right? And once bonded, it has 1, 2, 3, 4, 5, 6, 7. So 6 minus 7 is -1. Carbon normally has 4, and here it has 4, 1, 2, 3, 4, one from each of the bonds. 4 minus 4 is 0, so the formal charge of this carbon is 0. And then this nitrogen normally has 5, and it has 2 in the form of lone pairs, and 3 more from the bonds. So 2 plus 3, 5. 5 minus 5, 0. All right, now that we have the formal charges for every atom, for every resonance structure, now we're going to find out which one contributes the most to the resonance hybrid. And to do that, again, you want the one that has the least charge overall, and also, if it does have a charge, you want the negative charge to be on the more electronegative atom. So, the correct answer, I'm going to give you guys, actually, yeah, wait, you guys try it out. Sorry, my bad. So, if you can find out, given those criteria, which one's correct, well, good job. So, yeah, try it. All right, so the correct answer is resonance structure number 3. Okay, so off the bat, we should have known that it was either 1 or 3. And that's because they both have the least charge overall, right? This one has a +1 and a -2 charge. So like, even though that balances out to -1, that's not what we're looking for. Like, it has charges in places, and that's what we're trying to negate in this process. We're not looking for the like final charge. We're looking at the charge that's distributed throughout. Here, the charge is more distributed, and we don't want that. And really, we don't want any charge whatsoever. But in this case, 1 and 3 are the better choices because it's kind of less charge overall, if you get what I'm trying to say. And then finally, we use that tactic of having the more negative charge be on the more electronegative atom. And since oxygen is more electronegative than nitrogen based on the periodic trends, we want it to be there. And that's why resonance structure number 3 is the one that contributes the most to the hybrid. Alright guys, thank you so much for watching my video. I hope you found it helpful. Also, if you did like it a lot, then I wouldn't mind if you liked and subscribed. Also, yeah, all the best with your quizzes and stuff in class, and see you in the next one.